Hello. The paper that we were assigned is Mining High-Speed Data Streams by Pedro Domingos and Jeff Holton. Throughout this video, we will begin with a discussion on knowledge discovery systems, or KDDs, and talk about data mining and their limitations. Then, we will dive into Hofting trees. We'll talk about what the need for Hofting trees is, talk about the Hofting bound and the Hofting tree algorithm, and then dive into some theorems and definitions that will be useful for when we get into talking about the VFDT system, or the Very Fast Decision Tree Learner. Finally, we'll dive into the actual paper and the studies that they conducted on both synthetic data, in which we'll talk about how the synthetic data was created, and then we'll talk about the study in which they applied the VFDT system to real-world data.
Before we go into depth on the concepts discussed in the paper, I will first discuss the reasons for why such concepts were researched. A large part of data mining comes from the use of knowledge discovery systems, or KDD systems, which are designed to identify and extract valuable information from large volumes of data. The efficiency of these systems are constrained by three main resources: time, memory, and sample size. In traditional applications of machine learning and statistics, sample size is usually the major limitation. The resources needed to perform massive searches over data are available, but carrying out a massive search over the small amount of samples available often leads to overfitting. However, in data mining applications, the bottleneck is time and memory rather than the examples. The amount of examples for data mining is in such an oversupply right now that it is impossible to make use of all of the samples with the current KDD systems, which can lead to systems underfitting the data. In order to combat this problem, the development of highly efficient algorithms will become a major priority. Today's most efficient algorithms concentrate on mining databases that do not fit in main memory by only requiring sequential scans of the disk. However, these algorithms have only been tested on up to a few million examples. For many applications, a few million examples is less than a day's worth of data. Many banks, retail chains, telecom companies, and popular websites generate millions of data every day. Also, as the internet continues to expand and ubiquitous computing becomes a reality, our current data mining algorithms will not be able to keep up, leading to the growth of unused data without bounds. Even preserving the examples for future use can become a problem when moving them to tertiary storage, as data can be easily lost or corrupted during the process. With the source of examples becoming a constant open-ended data stream, mining just a fixed-size database seems questionable and inefficient.
Now we'll go over a bit of background. The need for Hofting trees. Hofting trees are based on decision trees. Decision tree learners are among the most commonly used classifiers in the field of data mining. To the right, we have a picture of the structure of a simple decision tree. Although they are very useful, they do have some drawbacks. The classic decision tree learners operate under the assumption that all training data can be stored in main memory. This means that there are memory-based limitations on the amount of data that can be used to learn from. Disk-based decision tree learners are a bit better. They assume that all training data can be stored on the disk. This means that they can learn from larger data sets, but they are still very limited. This brings us to the Hofting bound. The goal is to create a decision tree learner for very large, possibly even infinite data sets, where each example is read and processed only once and in constant time. This approach will make it possible to create much more complex trees. The idea is that to find the best attribute to test at a node, only a portion of the training data that passes through it needs to be used. The Hofting bound is used in order to choose the number of examples that are needed at each node. Here is some more information about the Hofting bound. For a real valued random variable r with range uppercase R, the Hofting bound states that, with probability of 1 minus delta, the true mean of the variable is at least r average minus epsilon, where epsilon equals the square root of capital R squared natural log of 1 over delta divided by 2n. N represents the number of independent observations of the variable R, and R average is their computed mean. The key benefit of the Hofting bound is that it is independent of the probability distribution that generates the observations. Here we have the Hofting tree algorithm. The Hofting bound makes it possible to say with a high probability, or 1 minus delta, that the attribute chosen with the smallest number of examples is the same as it would be with infinite examples. On the right, we have a picture of the pseudocode for the algorithm. It takes as inputs S, a sequence of examples, X, a set of discrete attributes, G, a split evaluation function, and delta, 1 minus the desired probability of choosing the correct attribute at any given node. It then outputs the decision tree, or the Hofting tree. Let G of X sub I be the heuristic measure. For example, a Gini index, information gain, etc. Assume that G should be maximized, and X sub A is the attribute with the highest observed G average after n examples, and X sub B will be the second best attribute. Let delta G average equal G average of X sub A minus G average of X sub B greater than or equal to 0 be the difference between their heuristic values. Then, the Hofting bound guarantees that X sub A is the best attribute with probability of 1 minus delta if n examples were seen at this node. And also note that delta G average will be greater than epsilon squared. It's also important to note that in the Hofting tree algorithm, there exists a null attribute in case splitting is worse than not splitting. From the previous slide, we see that the Hofting bound guarantees that X sub A is the best attribute with a probability of 1 minus delta. Once it is split at the current best attribute, the remaining examples will then be used on the new leaf nodes. This is the basis of the Hofting tree algorithm. Now we'll go over the memory that is required for the Hofting tree algorithm. Its space complexity is big O of dvc at each leaf, and big O of LDVC for the entire tree. D represents the number of attributes, V is the maximum number of values per attribute, C is the number of classes, and L is the number of leaves in the tree. Now we will go over some theorems and definitions related to the Hofting tree algorithm. The first definition is the extensional disagreement, or delta sub E. The extensional disagreement between two decision trees, DT1 and DT2, is the probability that they will produce different class predictions for an example. The second definition is the intentional disagreement, or delta sub I. The intentional disagreement between two decision trees, DT1 and DT2, is the probability that the path of an example through DT1 will differ from its path through DT2. Here we have an important theorem relating to Hofting trees. If HT delta is the tree produced by the Hofting tree algorithm with a desired probability of delta given infinite examples, and DT star is the asymptotic batch tree, and P is the leaf probability, then the expected value of the intentional disagreement between the decision trees HT delta and DT star is less than or equal to delta over P. This makes it possible to choose the maximum expected disagreement as input to the Hofting tree algorithm.
The Very Fast Decision Tree Learner, or VFDT, is a decision tree learning system based on the Hofting tree algorithm previously discussed. The VFDT allows for the use of either information gain or the Gini index as the attribute evaluation measure when making splits. It is I/O bound in the sense that it mines examples in constant time, which is faster than the time it takes to input them from disk. It doesn't store any examples or parts of examples in main memory, only requiring space proportional to the size of the tree and associated sufficient statistics. It can learn by seeing an example only once, which allows the system to not require any examples from an online stream to ever be stored. Also, it's an anytime algorithm, which means that a ready-to-use model is available at any time after the first few examples are seen, and its quality increases smoothly with time. The VFDT includes a number of refinements to the Hofding tree algorithm. These refinements include ties, G computation, memory, poor attributes, initialization, and rescans, which will all be covered next. The figure shown on the right depicts the initialization and growing process of a decision tree when using these VFDT refinements. When at least two attributes have heuristic measures, or Gs, that are very similar, there could potentially be a large amount of examples needed to decide between them with high confidence. This process is presumably wasteful, since the attribute chosen will likely make little difference due to the high degree of similarity. VFDT can optionally decide that there is a tie between similar attributes and split on the current best one if the change in the mean G is less than epsilon and tau, where tau is the threshold that is previously specified by the user. Recomputing G for each example takes up the most significant amount of time. It is inefficient to recompute G for every new example because it is unlikely that the decision to split will be made at that specific point. VFDT allows the user to specify a minimum number of new examples, denoted by nmin, that must be accumulated at a leaf before G is recomputed. This reduces the overall time spent on G computations by a factor of nmin and can make VFDT nearly as fast as if only the training examples were classified. Although, this implementation will result in a smaller delta than the one specified by the user, since examples will be accumulated beyond the strict minimum required to choose the correct attribute. A smaller delta would increase the time required to build a node in the tree, but the net effects of the refinement would still result in a speedup. While VFDT can process examples faster than they arrive, the main obstacle to learning arbitrarily complex models will be the finite RAM available. VFDT's memory use is dominated by the memory required to keep counts for all growing leaves. If the maximum available memory is reached, VFDT deactivates the least promising leaves in order to make room for new ones. The least promising leaves are the ones with the lowest values of PLEL, where PL is the probability that an arbitrary example will fall into leaf L, and EL is the observed error rate at leaf L. When a leaf is deactivated, its memory is freed, except for a single number that keeps track of its PLEL value. A leaf can also be reactivated if it becomes more promising than the currently active leaves. This is done by scanning through all active and inactive leaves at regular intervals, replacing the least promising active leaves with the inactive ones that are more promising. Memory usage is also minimized by dropping attributes early on when they don't look promising. When the difference between an attribute's G and the best attribute's G become greater than epsilon, the attribute can be dropped from consideration and have its memory freed. VFDT can be initialized with the tree produced by a conventional RAM-based learner, like K-nearest neighbors, on a small subset of data. The tree can be input as is or over-pruned to contain only nodes that VFDT would have accepted given the number of examples at them. This will allow VFDT to reach the same accuracies at smaller numbers of examples throughout the learning curve. VFDT has the ability to rescan previously seen examples. This option can be activated if either the data arrives slowly enough that there is time for it, or if the data set is finite and small enough that it is feasible to scan it multiple times. This means that VFDT never needs to grow a smaller tree than the other algorithms because of using each example only once. The next part of this presentation will go into an empirical study of VFDT, where the utility of these refinements is evaluated.
Now that we have some background information, we can begin taking a look at the actual empirical study that the paper covers. For this study, the researchers decided to compare the VFDT algorithm to C4.5, which is widely considered to be the industry standard for these decision tree-based models. There were some restrictions placed on the models to help simulate real-world conditions, such as the restriction of 40 megabytes of memory and the use of 50,000 examples used for testing. These were standardized across the two models that were used. There was first a synthetic study that was taken place using synthetic training data that was generated by the researchers. The generation of training data was done with the following parameters. There were 14 concepts, which are essentially just trees that can be sampled from in order to generate training data. There are 2 final classes, which the algorithm is trying to predict, and then 100 binary attributes, which are attributes of the data that can either be yes or no. How these 14 concepts were generated is that one of these binary attributes would be chosen at random, and then the data would be split amongst this binary attribute, with yeses going one way and nos going the other way. This then repeats until the node becomes a leaf node, at which it is randomly assigned one of the 2 classes. The generation of these trees had some stipulations that were imposed on them in order to ensure the quality of the data. The first of these is that you cannot use an attribute to split the data if it had already been used on that node's path from the root. There was also a minimum depth of 3, meaning that no split amongst the tree was converted to a leaf node before the 3rd level. Also, they had a maximum depth of 18, meaning that if a decision tree reached 18 splits amongst the data, then it was terminated then and there to become a leaf node. After these 14 concepts were developed, these were repeatedly sampled uniformly in order to generate training and testing data. After sampling from the decision trees, there was anywhere from a 0 to 30% chance that the node class of a leaf node would be flipped. This helps add noise to the data, ensuring that no 2 training trees were ever the same. As an example, let's look at what a tree generated using these rules would look like. We begin with 100,000 examples. Let's say that out of the 100 attributes that we have available to us, we decide to split on A1. All of the examples which have A1 as false go to the left, and all those with A1 as true go to the right. Then, we recursively repeat this process for each subtree. So, on the left, we would need to choose an attribute to split on. However, we cannot choose A1. The same goes for the right side of the tree. We can repeat this process for the true and false sides on the A77 split, deciding to split on A40 for when A77 equals true, and A31 for when A77 equals false. You'll notice that we can reuse splitting on A31 since it is not contained on the path up to the root node, and instead is on the other side of the tree. We want to prevent reusing attributes in order to help the model learn. After we've developed our first layer, some of the nodes will become leaf nodes and get randomly assigned to either the purple or red class. This is because we've reached our minimum depth of 3 layers. We can take the remaining nodes and split them off into a final layer. For the sake of the example, we can pretend that this is the 18th level of the tree, and therefore we need to assign every node either red or purple. Now we have a sample tree. When we sample this sample tree in order to get training data, depending on the noise value that is predetermined, we change anywhere from 0 to 30% of the leaf nodes to be the opposite color. That is how the training data was obtained for these 3 models. The 3 models that were used to train on these examples are as follows. There is the baseline C4.5 model, which was trained up to 100,000 examples, the VFDT algorithm, as explained earlier, and a VFDT bootstrapped version with an overpruned version of the tree that was produced by the 4.5 algorithm. The reason that we only use 100,000 examples for the baseline C4.5 is that 40 megabytes as the maximum memory constraint only allows for up to 100,000 examples to be used. Now, if we dive into the results that the researchers obtained, you can see that VFDT struggles with beating C4.5 in accuracy up until 100,000 examples. Again, this is the maximum number of examples that C4.5 can train on before using up its memory constraint. And so after this, the less memory-intensive VFDT can take over and continue to train on examples, further boosting its accuracy. VFDT Boost is also able to have a very good starting accuracy due to the bootstrapped C4.5 tree that it starts with. Looking at Figure 2, which describes the average number of nodes in the trees, VFDT and VFDT Boot always have trees with similar numbers of nodes, and that number is always smaller than C4.5. This just goes to show how VFDT is able to do more with less. Looking at Figure 3, we can see that VFDT-based models are way less susceptible to noise in the data. This level of competency is continued in Figure 4, where it can be seen that the VFDT algorithm performs better than C4.5 as the concept size, aka the amount of leaves in the tree, increases. Now moving from synthetic data to real data, the researchers began applying VFDT to mining the stream of web page requests that emanated from the entirety of the University of Washington's main campus. They collected data over a 1-week time window, in which they were able to correctly gather 82.8 million requests in order to use training data, with each of these categorized into one of 170 organizations. These included certain colleges, certain departments within those colleges, etc., etc. The idea is that this data can be used to improve web caching by predicting which hosts and pages will be requested in the near future, given the requests that were made previously. Finally, the testing data for this section was conducted using requests from the last day of data collection. Looking at the results, it's good to see that the VFDT algorithm is able to achieve around a 75% accuracy towards the end of the study as it trains on more examples, marking good progress for the algorithm's real use cases, such as the web caching example that was used previously. That concludes the main content of the paper that we were assigned to. As a recap, we went over KDDs and their constraints, and then, more generally, we went over data mining and the limitations that they have, which inspired the use of Hafting trees and the Hafting tree algorithm. We then went into the VFDT algorithm and talked about its improvements on the Hafting trees. Finally, we went over the paper's actual results, in which we compared the synthetic and real data studies with 3 different algorithms.